ಅದು ವೆಜ್ಜಿ ಸಸೆಗೋಳಿ ಮಾಡ್ತೆ ವೆಜ್ಜಿ ಸಸೆಗೋಳಿ ಬಿಲ್ ಚೆಕ್ ಮಾಡಿ ಸ್ಪ್ಲಿಟ್ ವೈಸ್ ರೂಪಾಯಿ ಮಹೇಶ್ ಬರ್ತೆ ಇತ್ತೆ 150 ನಾನು ಕೋರಿದ ಅವರ ಭಾಗವಾಗಿ ಕೋರಿದ ನಿಮಗೆ ಈರುಳ್ಳಿ ಎನ್ನ ಕೊಡೋದು ಅಡ್ಡು ದಿನದ ಪಲಾವ ಅವು ಅಲ್ಪ ಬೇರೆ 60 rupees ಒಂದು ದಿನ 30 rupees ಅರ್ಧ ಕಿಲೋ ಹಾಕೋದು 90 ಪ್ಲಸ್ ಈರುಳ್ಳಿ
Hello, Dinesh sir.
Hello. Sir, we can start, sir.
Okay, sir.
Yeah, I'll just.
So, welcome back, participants. We shall now resume our afternoon session of day 5, that is hands-on session in deep learning by Dr. R. Dinesh, research scientist at Samsung, Mangaluru. I request Dr. R. Dinesh sir to continue with the session. Over to you, sir.
Yeah, okay. So, thank you. Welcome back. So, I think after lunch, so it's difficult even for the face-to-face session. And I don't know, like online session, how effective it would be. So I have like, okay, so few slides left, like I'm almost towards the end of the presentation. So once we complete this presentation, we will go ahead with the hands-on session. So, so we were talking about the different trends, like, okay, so according to Gartner and different business magazines, like, okay, so they have identified what are the upcoming trends in the area of machine learning in general and deep learning in particular. So I collected few trends, and like, okay, we discussed few of the trends, right? Like, okay, so starting from industry automation, voice assistance, activity recognition, recommendation system, summarization, and effective marketing. So like that, like, okay, so the NLP and conversational AI. So this is another trend. So where, like, okay, so the especially the service industries, like, so they want to deploy chart customer queries and needs. So with respect to that, like, okay, so there is a lot of traction in the area of conversational AI, like, okay, which requires bringing in both language generation, like, okay, so the NLP, natural language processing. So it should understand, like, okay, so what the user is asking. So which is because when a person talks, right, like, okay, so there is a lot of ambiguity, like, okay, so unlike the written communication, the oral communication will have a lot of challenges to understand, like, okay, so one is the accent, the another one is like the slangs being used. So these are the kind of thing, like, okay, so the challenges, those challenges need to be addressed. And once so it understands the conversation, what he is asking, then it should identify appropriately, like what response it has to give. Like, okay, it's not like, okay, one way, it's a two-way communication basically. It need to understand the what is being asked, and then it should process that information and then identify appropriate solution, and it should revert back with the appropriate resolution for whatever the query is being asked in almost in a real time. So this is the challenge being like we looked at in the area of conversational AI. Lot of scope in the area, like we are developing a system. Like if some of you are planning to take up your research in the area of natural language processing, speech processing, and conversational AI. Like so try to consider lot of traction in this area as well. And another trend being looked at it is computer vision. So basically, like computer vision, all in all, like so basically we are trying to solve most of the computer vision problems using the CNN and deep learning. But especially like when I talked about the computer vision here, so there are two aspects looked into. One is the processing, or like so making the analyzing the images and videos at the cloud. So are the cloud level or the server level, where the information processing are like the service being offered as a video analytics or the image analytics as a service. Okay, basically you can write lot of services, and these services being hosted in the cloud, so where the customer comes with their images and videos, and you can support it. So for example, like so if the crime scene analysis, what the forensic department or the police department, what they will try to do is they will collect the videos from the surrounding the crime spot surrounding video feeds from the different CCTV installed, and they will upload those videos into the cloud, and they will ask for specific events to be recognized or identified in that video sequences. So you can always host your solution or the machine learning algorithm or the video analytics or the image analytics solutions on the cloud, and take these videos as an input and analyze and provide a solution. So that's what like so the cloud based solution. So a lot of development or like so the scope being forecasted in this area, especially like okay, so using the cloud services like AWS, Amazon Web Services, or the Microsoft Azure kind of things, where you can host your solution and like okay, you can advertise like okay, what kind of video analytics service you can offer, so that like customer can submit and you can support the analytics. And another aspect is like okay, so that is one aspect, and majorly like okay, so even today most of the deep learning solution what currently being done is mostly like either it is running in a PC environment or on the cloud environment. But going forward, what is required is like okay, so to expand the horizon of this computer vision solution, so we need to look at edge solution, edge processing. Edge processing means like okay, so for example, you want to detect the vehicle in, for example, you are considering autonomous driving. In autonomous driving, you cannot keep a PC in your car, or you cannot communicate a video feed onto the in a real time to the cloud server and get the feedback. So it has to be done. Everything should be done in a real time, in a close to the sensor. Okay, so in such case. These deep learning solutions need to be ported onto like a software on chip, and the GPUs or the onboard low cost GPUs. So when I say low cost GPUs, because cost is one factor, because when you try to implement these kind of solutions onto the edge platform, you are not afford to have like okay, so huge cost. Customer is not willing to spend too much of money on those kind of solution. So your solution including the hardware, it need to be very, very cheap. And at the same time, the solution should be processed in a real time or near real time in scenario. So for example, like if you're installing a driver detection, like driver activity monitoring or forward collision detections kind of solution onto using the deep learning, how do you port these kind of solutions onto a small board or a SoC? So that's what is very, very critical and tricky, because you cannot have a like okay, so entire most of the time like okay, for developing a deep learning solution we use TensorFlow or like okay, complete development deep learning development environment. But when it is come to like okay, so the inferencing, you don't have that luxury. You cannot host your entire solution or like okay, so even the deep learning platform environment platform onto your edge computing platforms. Okay. In such scenario, how do you take this model and put it onto the low-cost devices or SOCs and do the inferencing in a real time is what is very challenging. Okay. So for that also there are a lot of development, like okay, if you closely look into the NVIDIA's development, like okay, so they come up with a TensorRT kind of optimizer where like okay, you can directly take the model, trained model, and put it onto a specific GPU. Like okay, you can optimize and put it onto a specific GPU so that it can be readily take it and implement it onto the board. So you can put it onto the GPUs. Otherwise, like okay, even one can consider a FPGA kind of implementation where like so you can decide what kind of what is your model and architecture, and based on that, like okay, you can implement it as an FPGA. So that's what the main aspect. Like okay, so when we say computer vision, so there are like okay, so two aspects. One is providing a solution in a video analytics or image analytics as a service, that is from mainly from the cloud or a server environment, and another one is in the from the point of edge computing aspects. So both are important. So a lot of scope, like okay, so you are not offered to have like okay, very deep network architecture, like okay, it's a very computationally expensive computer network architecture. So then probably you need to also look into like getting the result is one aspect, and also how do you tweak the parameters and like okay, tweak the architecture in such a way that you can complete the processing in a very less memory footprint and less computation power. So that's what the two aspects one need to look into it. So that will also take a lot of forefront or driving seat going forward, at least in the coming years, for expanding the horizon of computer vision solution, especially enabled by deep learning technology. Okay. And of course, like okay, so one more aspect like which is going to drive is like okay, so how best we can extend it to the fields or the sectors which are untouched by technology yet. Okay, so mainly from the agricultural standpoint, agriculture, like okay, so there are some research being done, like okay, so develop the initial models or the initial solution for detecting the harvesting time or like kind of pest, those kind of scenario. But so still like okay, a commercial solution or like okay, large scale solutions are still not being done. So maybe like okay, so in the coming years this will also take the forefront. So to see like okay, how best we can take the solution to the technology where like agricultural sector, especially for enabling the computer vision solution enabled by deep learning. Okay. And of course, like okay, so the food processing sector is one sector where like okay, so the deep learning or the machine learning technology being successfully applied, at least like okay, so to some extent. So this will also like okay, so see a lot of traction going forward. So these are the major trends, like okay, so what has been identified for the year 2020 to 2023. So something like some technologies are like okay, so some sectors will go up to 2025, but generally like okay, so these trends has been identified will be the four driving factors, especially in the area of machine learning for next few years. Okay. Now, like okay, so if you look into the today's discussion, like okay, so we talked about we started with machine learning. I think just to touch upon the basic aspects, and then we start looking into the understood the challenges, main limitations of machine learning, conventional machine learning. When I say, so we understood like feature handcrafted feature extraction is one major bottleneck in most of the conventional machine learning techniques. Then we looked into like okay, how this challenge can be overcome with the help of deep learning. So in the deep learning, like okay, so there are two aspects, right? One is learning the features. So given a data, like okay, how best we can learn the features, and then like okay, so once the features are learned or extracted, like okay, so then we go for a conventional like okay, classification approach. So with respect to that, we studied a specific type of deep learning called CNN. Okay, so don't be under the impression CNN is the only deep learning aspect. Like there are multiple aspects. Like even without convolution, also you can still realize the deep learning technology, like deep learning, even for the numerical data and sensor data. But we looked into a very specific case of CNN. So with respect to that CNN, like, okay, we understood how the CNN works, and with the example, we understood like, okay, so what is convolution, how the feature aggregation and feature representation and aggregation happens, and how this entire thing can be clubbed as a end-to-end solution. And we also looked into a few standard architectures which can be used, like, okay, so already readily trained model can be taken and you can customize for your application. That also we looked into it, and we looked into the like major advantages of CNN. Also we understood, like mainly transfer learning and tweaking the network architecture, customization of the network architecture. You can start with the standard architecture or the standard model, and you can start customizing to your specific solution. That also we looked in. And then we looked into another interesting aspect of CNN called autoencoders, which can be trained to solve most of the problems, like, okay, so the compression or the dimensionality reduction, image reconstruction, and noise cancellation and segmentation, etc., and so forth. Okay, and then we looked into the different trends, recent industrial trends in the area of machine learning or deep learning for the next few years. Okay. So now, like, okay, so I just want to conclude this discussion by highlighting few of the research scope, like, okay, so some of the research problem in the area of deep learning. Okay, so like now machine learning problem, or like, okay, so solving machine learning is almost like, okay, becoming very simple task. Like, okay, now earlier machine learning used to be like, okay, very tedious job, mainly because of the you need to understand the classifiers, and you need to work on the handcrafted features, like it's a feature extraction and etc. and so forth. Now with the advancement in so many deep learning ecosystems available, like, okay, so you have like, okay, so TensorFlow, Keras, etc. and so forth. There are forget about like, okay, so not only the development tool, like, okay, so there are commercially and available and free platforms available where you can just load the data, like, okay, with the appropriate user interface. You can just load the data, you can select the drag and drop the model, create a network architecture, and train and build a model. So having said all these things, like, okay, so the solving, like, okay, so using machine learning technique for solving any specific problem is not that challenging or not that difficult right now. With one need to understand, like, okay, so what kind of tools and technology need to be used. So once you are familiar with that, building a machine learning solution for a given problem is not that difficult. Okay, of course, like, okay, so when it comes to, like, okay, so tweaking the final steps are a little tricky, but otherwise, like, okay, so one can easily build the first cut solution for their problem. But then are we at the end, actually, like, okay, so is there is any problem left in the machine learning or the deep learning? So I just identified few problems, like, okay, so which still, like, okay, so require a lot of uh, research need to be done to address these issues. The first issue is, like, okay, so we understood, right, like, okay, so your deep learning does wonder only with respect to the data, actually, like, okay, so deep learning becomes very efficient and effective, like, it gives the good result when you have, like, okay, so good amount of proper data. Okay, so data plays very important role. There are some sectors where, like, okay, so you can collect only limited data. For example, like, okay, so somebody was asking, like, okay, how to apply the machine learning for or deep learning for medical data. When it comes to medical data, so there are limitation where you cannot keep on extracting or collecting a huge amount of data. Unlike other sectors, medical sector has got some limitation in getting the data. In such scenario, how do you develop deep learning solution? How do you plan to use the deep learning solution for such cases where data is a scarcity? Like, okay, even we are talking about, we are in the era of like data explosion, where, like, okay, data is available everywhere. So there are fields, like, okay, so there are sectors where there is a collection of data is still critical or still challenge. So mainly from the or due to like the challenges, like because of the ethical issues. Okay. Okay, so how do you model, how do you build such deep learning system for such a sectors where data is a scarcity? Like, okay, so how do you model very good deep learning models with limited data? Okay, so that is one area, like what is very, very important. So there are some research being done, like, okay, so we have like, okay, something called generative models, where you can generate the data, synthetic data, by adding like, okay, so generative adversarial networks. And there are like, okay, so different augmentation techniques being tried out to augment the data. Having said all these things, but these augmentation and generation data, like, okay, so it's only accurate to like, okay, so whatever the data has been seen. But there are cases like, okay, so where different type of or different categories of data can also can occur. Okay, how do you build such model? Like, okay, so this is what one primary sector that one need to looked into. So how best we can build a good model, so with limited or less data. So that is one very interesting research, one can take it up. Okay, and so I don't know, like, okay, if somebody of you worked or looked into the generative models, right? So generative models, like, okay, so are good in generating the data. Like, okay, so basically, like, okay, so generative model works in the way, like, okay, so it try to generate the data. Like, okay, so we need to specify whether it is a fake or a real data. Like, okay, so the overall objective is you try to generate a data such a way that, like, okay, so though it is a fake data, it should be like, okay, so on similar or on par with the real data. So your model should, your classifier should not be. So there are two aspects. One is data generator, which will be keep on generating the data, and there is a classifier which will classify whether the data is a fake data or a real data. Okay, and your generative model, like, okay, so the generator is successful when it keep on generating the data which is similar, when your classifier failed to recognize it as a fake data. Okay, so that's the kind of mechanism. But how do you control that actually? Like, okay, how do you control these generative models to generate a data in such a way that, like, okay, so all possible variations are being added? Okay, so it's not like, okay, so biasing to generate, okay, so replicating the real data. So this is what, like, okay, so another interesting field where, like, okay, so one can look into it. How do we control the generative model not to replicate the original data, but to add variations to the data such a way that, like, okay, so your data looks almost like, okay, so realistic. Okay, and yet another problem is uncertainty quantification. Uncertainty quantification is probably like, okay, in the final stage of classification, we use the softmax, right, to classify the sample, whatever the sample, like input sample, into the class to which it possesses the maximum probability. So now let us assume, like, okay, so there is a uncertainty 0.51 is the probability, there is a highest probability what we got. Okay, then how do you classify it? Like, okay, so are you confidently classify that, okay, this is 0.51 belongs to class 1, okay, hence I am classifying it to class 1? It's not acceptable, right? Like, okay, so you are only 51% confident, or like, okay, so the scores are not very, very significant. So yet, so we need to quantify, like, okay, so if you are not able to confidently classify into one class, at least you try to quantify what is the uncertainty, where we are trying to miss it actually. Like, okay, so that's the kind of uncertainty quantification is one interesting research. And in this area, like, okay, so there have been, like, okay, so some work being done, like, okay, so to identify, like, okay, so the activation, like, okay, so where, like, okay, so the what kind of features being learned, so what areas has been considered, looked into, like, okay, while doing the classification in terms of the class activation maps and etc. and so forth. So again, like, okay, so some research can be done in the area of uncertainty quantification. And yet the major problem, like, okay, so the major problem, like, okay, so in both in conventional machine learning as well as in the deep learning, so given a data, you extracted the feature, like, okay, and do the classification, you did the classification, and like, okay, so your classifier worked, like, okay, so for whatever the grace, like, okay, so your classifier is working properly. So for a given data, training data and your testing data, when you test it, so it is giving 99%, but there is no mechanism to explain, like, okay, why my model worked, on what basis it worked, like, okay, whether it is really learned, like, okay, so because from the data it is telling, like, okay, yes, it is working, like, because I tested with sufficient data and ensured that, okay, so my model is working properly. Okay, so that's how I convinced that, okay, so my model is decently performing well on even on the testing data. But there is no mechanism to explain why my model worked. And there is no mechanism at the same time on the other end, if your model didn't work right, and there is no way to explain why my model didn't work. Okay, interpretability is the main problem with most of your deep learning and even in the machine learning problem. Like, okay, so we don't know, like, okay, so why, at least in machine learning, conventional machine learning, at least you can see, like, okay, you can plot your features and try to see, like, okay, whether your data is separable or not separable, and etc and so forth can be done. But when it comes to deep learning, right, it's a completely, like, okay, encompassed, like your feature extraction and the classification is tied together. So you have very limited scope to explain it. Okay, how do you interpret, like, okay, why my model worked, why my model didn't work? So that explain, like, okay, so interpretability is one major issue. So in this aspect also there have been some work being done, so especially in the like, okay, so explainable AI or so that's what, like, okay, so even Google is trying out, like, okay, so how to build the model, how to explain, like, okay, so why model worked or not worked, etc. So yet another area is like hybrid deep learning. Like, okay, how do you bring in different data formats itself? Like, okay, so for example, I have a different types of data. So that means, like, okay, so there is a image followed by, like, okay, so the additional data about, like, so what kind of data it is. Like, okay, so in terms of so image caption or etc and so forth. How do you bring that different modality of data, and how do you incorporate into one framework? That is another area, like, okay, so hybrid deep learning. You got it right. Basically, for images or videos, we use, like, okay, so the CNN. So if it comes to text or other data, like, probably CNN doesn't work. Probably we need to use other type of deep learning technique. So now I can always train it as a two different models, and I can combine it at the score level or at the data levels. But there could be a scenario, like, okay, where I can, if I can combine these data at initial levels itself. So then probably, like, I can build much better deep learning systems. So this is another area, like, okay, so where people are trying to see, like, okay, so how the different feeds can be taken and, like, okay, so combining at different levels, like even in the starting at the initial levels of machine learning. So that is a very interesting research problem one can consider. And another problem is, like, how to extend the machine learning technique for safety critical applications. Safety critical applications, because this is again has got a link to the uncertainty quantification and interpretability. Unless, like, okay, you know why your model worked. So there is a there is a large amount of skepticalness, like, okay, in adopting that solution. For example, like, when I say safety critical application is, like, okay, so assume, consider it like missiles. Like, okay, you want to have a you have a guided missiles and you want to leave it to the deep learning system. So then, so probably, like, okay, so defense will not never accept this kind of solution, because unless you explain, like, okay, why your model is worked right, so they may not be able to accept this kind of solution. So these are the there are safety critical, mission critical applications, so where still people are hesitant to successfully, like, okay, so embracing this machine learning technology, mainly because of the limitations in, like, okay, are the challenges with respect to the uncertainty quantification and interpretability. And another interesting research problem is with respect to the edge computing. Okay, edge computing, as I said, right? So basically, we need to move our execution or the inferencing close to the sensor. Okay, so when it comes to the close to the sensor, so you have very limited power. Limited power in the sense, like, okay, so basically it should consume less power. Okay, because it has got a very less number of gates and, like, less number of GPU cores, and it has got a very limited memory footprint. Okay, so I cannot tell that, like, okay, I will use ResNet 150 layers ResNet to solve a problem, because it will not definitely it will not support, because you don't have enough memory to support that one, and also you don't have enough number of GPU cores to process that data. Okay, in such scenario, still I need to get a very good result, but how do you optimize it? Okay, so how do you optimize your model or the network architecture to specific GPU hardware? So as I said, like, okay, so there are already some solutions available, like in terms of TensorRT and other things, like, okay, where you can specify the target GPU, so it will optimize. But that is like, okay, again, like, okay, it's just like code optimization, right? So optimization done by a machine. So users still need to look into, like, okay, so what is the effective architecture? What kind of architectures are, like, from the network architecture level? How we can decide, like, okay, so these are the minimum number of filters are required, like, okay, so this is the minimum number of convolution layers required, etc., and so forth, even before we start defining the training the model. So that's where, like, okay, so the edge computing or supporting this AI solution in the edge platform will be, like, okay, very, very interesting and very challenging environment. So definitely some research can be taken from that point. So where, like, okay, one can investigate and identify, so what is the network architecture which take, like, okay, less memory footprint and less GPU power to solve the problem. So I felt like, okay, so I'm sure, like, okay, there are definitely, like, okay, so much more problems in this area, like, okay, so these are the few problems which comes to top of my mind, and I just captured it in this sense, like, okay, so these are the some of the problems one can certainly take for their research problem. So which is quite interesting, and still, like, okay, so a lot of contribution can be done in the area of deep learning. So I think with this, if you have any questions, like, okay, so I'll just take up the questions, and then we'll move to the hands-on session.
Thank you, sir, for such a wonderful session. We have some questions.
Yeah, yes.
First question is, if we have a data set, so which approach is better? That is, whether we have to go for transfer learning or training from the scratch?
So it depends. Basically, if your problem is, like, okay, so fits into the similar category of any of the standard architecture, you can always take that standard architecture and try to see, like, okay, how well it is performing. If it is not performing well, then you can always start customizing. You can do the transfer learning. So you can start with initial model and start doing the transfer learning. Okay, so that is one approach. Like, but the second thing is, like, okay, so if your end target, like, basically you need to port this solution onto a low cost hardware. So then obviously, like, okay, so your standard architecture doesn't fit into your network architecture, right? Or your limited hardware resources. Then probably I would suggest you try to take a look into the network architecture itself. Try to see, like, okay, what is the number of parameters, number of trainable parameters. So where it is taking the huge amount of memory, and start customizing or start optimizing at the initial stage itself, so that you don't spend too much of time. Like, basically, if you start with your end objective is you want to put it onto a low cost hardware, but if you take a ResNet on a PC environment, it may give very good results. But when you start porting it, like, okay, you need to rework from the beginning itself. So first you try to decide what is the end objective. With respect to that, you start working. But if you are working on a PC environment, and if there is no constraints on the memory and the computation environment, right, computational platform, so then probably you can always start with the standard network or standard model or the pre-trained model, and then do the transfer learning.
Next question, sir. For classification, how will we know that which feature is used by the network to learn?
Okay, so that's what, like, okay, so I was talking about the interpretability, right? Like, okay, so unless, like, okay, you try to tap in, so there is no way, like, okay, you know that, like, okay, so what features or what sectors of the images have been considered for the training. So there are some aspects, like, okay, so where you can visualize it actually, like, okay, so class activation maps. So which will highlight, like, so what part of the images or what kind of data has been considered, or, like, while doing the classification, those things you can visualize. Okay, so there are, like, okay, nice visualization tools are available, like, okay, so you can use them to see when you try to do the classification, which particular part of the image or which particular filters or the sectors of the images have been considered, that you can visualize it. So with the help of CAM. And as I said, like, okay, so a very interesting problem is, like, okay, so still you can always look into the interpretable AI or the explainable AI. So now you can start looking into the research actually. What are the new developments in that particular area? There are certain tools definitely available, which is implemented into the standard platforms also, like in terms of CAM, that you can use it for the initial case. At the same time, you can start exploring from the point of explainable AI.
Next question, sir. How ML, DL, and AI are interconnected?
See, basically, AI is a superset. So, artificial intelligence is a whole bigger umbrella. So, where we are talking about the complete intelligent system, okay, which encompasses like, okay, so not only the machine learning, like, okay, even cognitive systems and neurocognitive systems and everything. So, definitely, artificial intelligence is a bigger umbrella. So within that, like, okay, so the machine learning, we are focusing on a very, very specific problems of classification and clustering, grouping of the data in the area of machine learning. Within that machine learning, like, okay, so in the deep learning, we are trying to see, like, okay, so there are certain challenges in the machine learning. So still we are like, okay, so we are trying to focusing on how best those problems, like, okay, so the feature extraction and other things can being solved with the help of deep learning. And this, like, okay, so this calls me like, okay, so very interesting question. Like, okay, so the with the deep learning, so can one can always think like, okay, using the deep learning or just forgoing the conventional machine learning is the question, right? So one need not to use the machine learning, but answer here is if you have a proper data, so sufficient amount of data, then you go for deep learning. If your data is very less, so for example, like, okay, so if you are having only 100 samples or 200 samples or very limited number of samples, so don't even try to venture into the deep learning. Okay, so in such cases, so it's still better to go with conventional machine learning, because you can always bring in the domain expertise to extract the features. Like, okay, so with the limited data, you know, like, okay, so what is with the particular domain, so you can incorporate that and extract a specific set of features to build a model. Okay, if your data is a scarcity, if there is a limitation in getting the data and a proper label for the data, like, okay, so still you try to go for the conventional machine learning. If you are having a sufficient amount of data and there is a mechanism to collect a lot of data, so then you venture into deep learning. So if data is a scarcity, don't directly jump into the machine learning, deep learning. So if your data is samples is only 100 and you try to use like, okay, so ResNet, so definitely it will not give a good result.
What is the minimum number of image samples to carry out deep learning based research?
See, basically, like, I think this is the data problem, like, okay, so both for the machine learning as well as the deep learning. So more than a data, so the quantity of the data, so quality of data is also very important. For example, like, okay, assume that you collected 1 million samples for training. Okay, so you are having like, so 2-class problem, like, okay, so you are having like 0.5 million for class 1, 0.5 million for class 2. Okay, so you are collected like, okay, so 1 million data samples. And if your data is like, okay, so more than 30% of your data is noisy. When I say noisy, your labels are noise. That means like, okay, so my problem is to classify the images into two categories: defect category and non-defect category. And while performing the labeling, while generating the ground truth, you might have spent like, okay, so labeled in such a way that like, okay, so more than 20% or 30% of your data is noisy data. Okay, in such scenario, so definitely like, okay, so neither conventional machine learning nor deep learning will give you the better results actually. Okay, unless you have a mechanism to reject those outliers or like rejecting that noisy labels, so your solution will not be very, very appropriate. But coming back to the specific question of like, okay, so how many number of images, right? At least like, okay, don't even venture like, okay, so if your data is like less than at least 5 to 10,000 of images, right, for per class, don't even venture into deep learning case.
Next, what about data augmentation for improving the number of samples?
Yeah, so there are two ways you can always augment the data. One is you can augment using the generative model. So, but problem is like, okay, so you are going for like generative model for generating additional data. If your data itself is very less, you want to generate, you want to train your generative model. Your generative model will not going to give like, okay, so good result. Even for the training the generative model also, you need to have a good amount of data. So with that data, you can always, if it is possible, like, okay, so you are having sufficient data to train your generative model, And with that, like, okay, if you are able to generate the generative synthetic data, then it's fine. Otherwise, you try to incorporate the domain expertise. See, for example, in case of classification of outdoor and indoor scenes, right? You can always bring in like your domain expertise. Like, so typically in the indoor, you can control the illumination. Like, there are computer vision algorithms, the image processing algorithms where you can bring in the illumination control or the contrast controls, or you can add like, okay, different type of noise. Like, so if it is a low light condition and a bright light condition, what kind of noise will be more prominent? Those kind of techniques can be incorporated while generating the augmented data. Okay. So having said all these things, augmentation data is good to address the problem of less number of training sample, but if it is possible, try to collect as much of data from a real field. That would be more appropriate, because if it is a defect data, like, okay, you are trying to generate a synthetic data for a specific type of defect, so there is no guarantee that it will generate all possible real kind scenarios. So it's always better to get a real time real scenario data. But if there is no scope, right, no choice, so then always you can go for a generative model, or even incorporate some kind of domain expertise while generating the augmented data.
Okay, sir. So we'll continue with the sessions.
Yeah. Okay. So for the hands-on session, like, okay, so I will be using TensorFlow. So so you are able to see the screen, my spider window.
No, sir.
No.
Only the PPT we can.
So now you are able to see, right?
Yes, sir.
Okay. So as I said, like, okay, I will be using Keras with TensorFlow. So the version I am using is just a minute. So the Keras version I am using is 2.1.4. Okay, and so it's a quite old version. So this is what I'm using. Like, okay, so the Keras is 2.1.4 and TensorFlow is 1.2.1. Okay, so if anybody want to start, like, okay, so I would suggest you can download Anaconda package. So from there, like, okay, you can get Python and other necessary packages. On top of that, you can install Keras, TensorFlow, and probably you need to install OpenCV to do the CNN kind of activity. So that's what I would suggest. Okay, so so other way, like, okay, so if you want to parallelly run this code, right, I would suggest you can use the Google Colab. Okay, you can just log into your from your account, Google Colab, and from there, like, okay, you can start typing this syntax so that you can parallelly run it. So all of you are familiar with using Google Colab, right? Or should I need to show how to launch? Okay. So if you are ready with any of this environment, right? Like, okay, let me know so that we will I will start explaining the code, and then we'll try to run it and see the results.
Sir, you proceed, sir.
Yeah. Okay. Okay. So the first one is like, okay, I'm trying to use the conventional neural network. Like, it's not a convolution neural network. Like, it's a conventional neural network. So this is being used for solving the handwritten digit recognition. Okay. Problem is, I have taken the MNIST data. So MNIST data, I think all of you are aware. So it's a handwritten numeral data. So which has got about 60,000 images. Okay. So each image is of size 28 by 28. So these are the handwritten numerals. Okay. So the numerals are written 0, 1, 2, etc. 9. So these are cropped and created like, so this is the standard data set. You can just like, okay, with the Keras, you can just download it. Okay. So in this, basically, these are the some of the import libraries. I'm just importing NumPy and from the Keras data set. Like, okay, so in the Keras, there are standard data sets already available. Okay, you can just if you install the Keras, right? Like, okay, so some data set you can easily get it. Like from Keras data set, I'm importing the MNIST. Okay, from Keras.models. Okay, so this is what the model. So sequential. So when I say sequential, so it's a feed forward network. So I think all of you are familiar, right? Like, okay, so I think yesterday I might have discussed. So in the neural network, there are two different types of more than two types actually. So you have a feed forward network and feedback network. When I say like, okay, so sequential, it is a feed forward network. Okay, the information flow will flows from input side to output side. And sequential means like, okay, so I'm trying to use the feed forward network. So from layers, like, okay, so dense is like, okay, so I'm trying to use the fully connected, like, so fully connected layer. So dropout, so it's a regularization parameter. Like, okay, so basically we are trying to tell like, okay, so randomly drop certain amount of neurons, okay, or certain parameters from the learning. So that's what the dropout. And some utilities I'm just importing it actually. We'll see like, okay, so when we start using it, I will just explain that. Okay. So next, I'm trying to randomize it. So I'm just trying to initialize the random seed to some seed point. I'm just loading the data. So from the MNIST.load data, which will load the data into training set as well as the testing set. Basically, this MNIST data standard data set has got two set of folders. So one is for the training data and another one is testing data. So training data is the data which we are going to use it for training the model. And once the model is trained, we are going to evaluate the performance on the test data. Okay. So basically like, if I run up to this point, so so it has got 60,000 training samples. Okay, each of size 28 by 28 image. That's what I said. So totally we have 60,000 samples, 60,000 images, and the image dimension is 28 by 28. Okay. So similarly, for testing, we have about 10,000 images. So we consider about 10,000 samples for testing this, testing the performance. So since I'm not using any convolution neural network, what I'm trying to do here is I'm converting this 28 by 28 image into a one vector actually. Like, okay, so 780 pixels. Like, okay, all these pixels are concatenated and we construct like, okay, so one dimension vector. So totally like, okay, so 28 by 28, it is 784 pixels actually. So 784 pixels. Okay.
Excuse me, sir. There is a request.
Yeah. Yes.
Sir, can you zoom the code? It seems.
I got it. Is it better now? You're able to see?
Yes. Yes, sir.
So don't worry. Like, okay. So if you are able to run it now, you try to run it. Otherwise, I will share all these codes. You can just run it offline also. Okay. So basically try to understand. So what we are trying to do, because this is only a type problem. Like, okay, so this will not solve any specific challenging problem, but these concepts can be used to solve any specific, like, okay, so any challenging problem. Like, okay, so try to understand what actually it is doing, so that like you can use it for different application or to solve your own problems. Okay. Okay, so basically, like I'm just computing the number of pixels. So that's what 784. So now I am trying to reshape this data. So whatever the data 28 by 28 image, right? I'm trying to reshape it into one dimension vector. Okay, so here I am trying to extrain dot reshape, extrain data into number of pixels. Number of pixels is nothing but number of rows into number of columns. This is what the number of rows and number of columns I get it here, the number of pixels. So basically this will convert your all the images into 784 dimension data. So let me explain and show you like so what exactly it does. So initially now after the extrain shape, so now you are having 60,000 rows and 784 columns. Okay, so earlier it was a 28 by 28 image data. So when we initially loaded, so this was the shape, right? 60,000 samples, each of 28 by 28 image. Now we convert that data into 60,000 samples with 784 rows. Okay, so sorry, 784 columns actually. So it's a one dimension vector now. Okay, and I'm just normalizing this data because image this is a grayscale image, so usually intensity values ranges from 0 to 255. I'm just trying to convert this data into 0 and 1. Okay, so by dividing it by 255, so we are just normalizing it. And so similarly, so it's a one not encode output. Like so, basically it's a supervised learning we are trying to do, right? So we have downloaded both X data and Y train. Y is a Y parameter. Okay, so let us look into like so. How does this Y data looks like? Okay, Y dot shape. So this is what it is only like one not code encoding. So it is a 60,000 samples. So how it looks like? Okay, so this is how it. Okay, so we have totally 60,000 samples, right? So this 60,000 samples, and what is the number of classes here? So since we are working on a numeral, so it's a 10 class problem. So basically like what is the, sorry, this is X parameter. So sorry, I should have shown you it. So this is how the data looks like. Okay, so the first data is from class 5. So the first, second one is from 0, 4, etc. and so forth. So these are the class labels. Okay, so you have X data and corresponding Y data. Okay. So this Y data, I'm just trying to convert into categorical data. So to make it as a one not code encoding. So basically, I'm just trying to convert it into a vector, a 10 class vector like this. Okay, so the first sample was 5, right? So I'm just trying to make 1 and remaining all are zeros, one not code encoding. Okay, so this is only like, okay, so for the sake of computational simplicity, I'm just trying to computational convenience. Actually, we have converted into one not code encoding. So the number of classes is 10. Okay, so that's what we're trying to do here. So number of classes here is 10. Now, since I'm using Keras, we'll try to see like, okay, how the network architecture. Like, okay, so it's very simple, very straightforward. Okay, so you need not to spend too much of time in implementing or coding anything. Like, okay, so it's very straightforward and very easy to define the network. Okay, so I'm just trying to define a baseline model. So this is where I'm trying to define the network architecture. So the model is a sequential model. So basically, I'm trying to tell it is a feed forward network. So it's a feed forward network I'm using. So I'm just adding the first layer. Okay, add model dot add dense. This is your first model layer, means it is a your first hidden layer. I'm just adding the hidden layer. We'll come to that. Like, okay, so why I'm just adding the first hidden layer, model dot add dense. Dense means like, okay, so basically like the connectivity from your input layer to this layer is fully connected. That's what the meaning here. Okay, it's a dense model. So how many number of like, okay, so the neuron should be there in this particular layer, I'm trying to define. Okay, the number of neurons in this particular hidden layer is equal to number of pixels. Okay, so what is the number of pixels? I have calculated here is a number of rows and columns, right? It is a 784. Okay, that means in my first hidden layer I have 784 hidden neurons. Okay, input dimension, so it is like, okay, so it will try to take the input dimension. So you need not to only for the first hidden layer you need to specify this. Input dimension is again like, okay, the number of pixels. Okay, basically what it is trying to tell is, so your input layer has got 784 neurons, and hidden layer also I'm trying to define the same number of neurons. Okay, so kernel, so basically like, okay, so we need to initialize the weights, right? Initial weights. Okay, I am trying to initialize the weights. Okay, so what is the dimension now here? So I have 784 neurons in the input layer, and I have 784 neurons in the first hidden layer. So totally, and it is fully connected. All these neurons, each input neuron is connected to every neuron in the hidden layer. That means, so all 784 neurons in the input layers are connected to all 784 neurons in the hidden layer. So totally, it is 784 cross 784. So that's what your weight matrix between these two layers, input layer and the first hidden layer. Okay, this particular weight matrix need to be initialized initially. I am trying to initialize this to random numbers coming from a normal distribution. So kernel underscore initializer is a initialization technique. Like, okay, it will try to initialize the initial values of the weights to a random number coming from a normal distribution. Okay, and so within that, like, okay, so in the activation layer, like, okay, so in the hidden neurons, each hidden neurons will have an activation called ReLU. I am trying to use here the activation as a ReLU. So as we discussed in the morning, right, like there could be possibly many different types of activation, like, okay, so sigmoid, tanh, etc. So here I am using ReLU as a activation function. Okay, clear? So basically what I'm trying to define here is I'm trying to define a network architecture in such a way that I'm trying to define a model is a feed forward model, feed forward network. I am adding first hidden layer. So you can observe here, like, okay, you need not to specify a specific for input layer. You need not to specify you need not to create a layer for input. Okay, so input will be automatically taken care. So where we are specifying here, input dimension is number of input pixel. So by specifying this, it will automatically take, like, okay, so the number of neurons in the input layer is 784. Okay, so with this, now I completed adding one hidden layer. So what it says this. Okay, so I have a hidden layer with 784 neurons. I want to initialize all the weight vectors, weights from the normal distribution, and I'm going to use the activation as the ReLU. Okay, so then I add the next layer. Okay, model dot add means like it will try to add the next layer. Okay, model dot add. So now I am trying to add the output layer now. Okay, model dot add dense. Okay, so again I am trying to say it is a fully connected. Dense means it's fully connected. So the number of classes is, because output layer I need to define how many number of neurons should be there, right? So in the output layer I am having 10 neurons, because this is output layer. The number of neurons in the output layer is equivalent to the number of classes. Okay, here I am specifying number of classes. Model dot add dense, number of classes is 10. Again, like, okay, so what is the dimension here? The weight matrix dimension. So I have 784 hidden neurons, and all these 784 neurons are connected to all 10 neurons in the output layer. So it is 784 cross 10. So that's what the weight matrix between these two layers. From input to first hidden layer, it is 784 cross 784. From the first hidden layer to output layer, it is 784 cross 10. I am trying to initialize it to, again, like, okay, so all the weights are initially initialized to random number from a normal distribution. Here I am using a activation of softmax. Okay, why? Because here I am trying to do the classification. That's the reason I'm trying to use the softmax, because I want to classify the sample into the class to which it possesses the maximum probability. Okay, so hence I am using the softmax, and then I am almost done with building the network architecture. Now I am trying to compile the model. Okay, model.compile. Loss. Loss means like, okay, what kind of learning rule I need to use. Okay, so since my problem is a classification problem, I am using categorical cross entropy as a loss. Okay, if somebody is working on the regression problem, you can use like, okay, so mean squared error. Okay, different type of loss you can consider. Like, okay, so here, since we are working with the classification problem, I'm trying to use categorical cross entropy. Optimizer, I'm trying to use a variant of gradient descent algorithm called ADAM. Okay, and metrics means like, okay, so what kind of metric? Like, okay, so what is the metric I'm going to use? Like, okay, so how well my model is performing? I'm using the accuracy as a metric. Okay, so similarly, one can use like, okay, different metric like precision, recall, etc., and so forth. I'm using accuracy here. Okay, so now I build the model. I specify what kind of loss function I need to use, what kind of optimizer I need to use, what kind of metric. I'll just return this model. So here, like, okay, I'm just calling this function baseline model. So this will return a model. So now model is ready. What I'm trying to do is model.fit. Model.fit means I'm performing the training process. Fit the model now. Okay. So with what? So use the training data, X train, Y train. So this is what my X parameter and Y parameter. So we need to have the validation data. Like, okay, so if you can define like, okay, so your own validation data set, right? So to see like, okay, so how well your model is converging, you can use the validation data set. Here, for just for sake of simplicity, for the validation, I'm using the test data itself. Whatever the test data we loaded, right? I'm using the test data for validation. So just for simplicity, like, okay, so the number of epochs have been set to 10. Batch size is set to 200. So batch size means like, okay, so in a batch, whenever like, okay, you try to take the one training, right, one iteration, how many number of images need to be considered for each batch? Like, okay, I'm trying to take 200 images in one batch. Okay, that means the 60,000 images are grouped into like, okay, so the different batches. Each batch is of size 200. Okay, so that means at a time it will take 200 samples and try to perform the fitting. Okay, and finally, so once the model is fit, so then I'm trying to evaluate the model here. So here, like, so basically model.evaluate means I'm trying to test the model. So what I'm trying to test, like, I'm using the same validation set, actually, whatever the validation set or the testing set, right? I'm using the same test to train to test the model performance. And these are like, so the few statements to print the baseline error and so prediction accuracy, etc. and so forth. Okay. Clear? So here I have not used any CNN. I am just using like, so conventional neural network actually. So it's a conventional feed forward neural network. So my network is very, very simple. So it has got one input layer with 784 neurons and one hidden layer with 784 neurons. It is fully connected. And I have like, so one output layer, like, so with output layer with 10 neurons. So let us just try to run it and try to see like, okay, so it won't take much time because it's only like 10 epochs. So you can see here, like, okay, so just now we completed one epoch. You know what is epoch, right? Epoch is like, okay, so one complete scan of entire data set. Okay, entire training data set. So once we scan the entire data set, so we have like, okay, so one epoch. So the first epoch completed in 14 seconds. The loss is 0.278. Accuracy is 0.92%. Validation loss, like, so this is on the loss on training data itself. On validation, like, on the validation data set, that's a testing data set, the loss is 0.14 and accuracy, validation accuracy is this. Okay, so as you can see, like, okay, so as the number of epochs increases. So in the second epoch, the loss is continuously decreasing. That means it shows that, like, okay, so the model is getting converged. Okay. Okay, so we almost completed. So with 10 epochs, so basically what it says is, like, okay, so your training loss is 0.0082, okay, and accuracy is 99.85%. That means when you train and test with the training data sets itself, like, okay, so it is 99.85%. When you test it on the testing data set, so its accuracy is almost 98.23%. Okay, so with very simple network architecture, with only 10 epochs, probably if you increase the number of epochs to maybe 25 or 50, probably you can even get, like, okay, so close to 99 or 99.6% kind of result. So we are able to get, like, okay, so 98.23% as the accuracy. Okay, so this is what the baseline error is, like 1.77%. So this is the error, overall error. So this is how we can implement a neural network for any data, actually. Like, so this I just explained with the MNIST data. So you can pretty much use the same kind of approach for any data. So if you want, I can just quickly run through the another data set, so which is a non-image data. Okay, so this is a primer diabetic data set. So it's a data set which talks about, like, okay, so the diabetes in a pregnant woman, actually. So it's a 8-dimension data. It has got 8-dimension data. So like pregnancy plus pressure, skin test, like, so some medical parameter. These are the arguments or the features. Okay, and this is the class level. See, for example, why I'm trying to show this is, like, if somebody wants to, like, okay, so work on the non-image data, right? So if you have extracted the data in CSV format, like, you can still, how the data looks like, I will just try to show you. I think most of you might have seen this data. Like, okay, so this is the data. So basically, this is having 8 features. This is feature 1, feature 2, feature 3, feature 4, 5, 6, 7, 8, and the 9th column is a class label. Okay, so whether it is prone to diabetic or non-diabetic. Okay, so this is the class label. Okay, so both are available in a single data, single file. So first, what you need to do is you need to segregate this data. Okay. So that's what I'm trying to do here. What I'm trying to do is, so data frame, I'm trying to read from a CSV file. So you can also, like, okay, if your data is available in Excel or CSV format, you can just load the data. Okay. So now, so from 0 to 7. Okay. So 8 means, like, with the 7, the first 8 attributes correspond to X variable, and the last column, the 8th column or the 9th column, is corresponding to the Y parameter. So Y8 means, like, okay, because in Python, index starts with 0. So that's the reason. Okay. So X and Y parameters are segregated. So number of classes is a single, it's a binary class problem. Again, here I'm trying to define the model in the similar way. So feed forward network. So the number of hidden neurons is, like, so exactly similar to, like, okay, so 8. Okay. And number of input layer, like, so it's again 8. Initialized to normal, from the normal distribution, activation is same. So the hidden layer, sorry, output layer has got only one neuron, so it's a binary class problem. So here I am using again the softmax. So categorical cross interpret, almost all the network exactly same network I'm using. Okay, only thing is, so it has got 10 neurons in the 8 neurons in the input layer, 8 neurons in the hidden layer, and 1 neuron in the output layer. So just try to run it. Should be pretty fast. So here also you can see like, okay, so the loss is decreasing, showing that, okay, so the network is converging. Okay, so so this is how it looks like. Okay, so we just run for the 10 iterations, so 10 epochs, and the overall loss is 1.81%. So we're able to get 0.981. So probably like, okay, so the either network is not very optimal. Just for the sake of explanation, I have used it. So two things can be inferred from here actually. So one is, if you are having image data and you don't want to use the CNN and still you want to use the conventional neural network, either you can convert that into pixel and you can still feed it. So that's what, like, so the number of parameters we were discussing in the morning session, right? So that's how it will work. Or else, like, okay, if you are having the features already extracted from in some or the other form, so you are having Excel data, Excel file, right? So you can still use this kind of network architecture. And how to build the network architecture, that's also I have shown actually. If you want to add one more hidden layer, you can still add it, and you can change some of the hyperparameters, and you can still get experiment with the different hyperparameters and different number of layers, so that you can get better results. Clear? So now, like, let us try to see like how to implement the CNNs. Again, I have taken the same problem. So the problem is like I have taken the MNIST data set. Okay, so it's again the handwritten numeral data. So exactly similar to the first one, but only thing is, in this case, instead of using the conventional neural network, I will be using the CNN for solving this problem. Okay, so I'm importing the NumPy, and these are the some of the standard packages I'm just importing. Sequential tells that it is a feed forward network. Dense, dropout, flatten. Okay, so basically this is the layer which tries to convert your two-dimensional data to a one-dimension vector. So basically, like, okay, once the feature extraction is done, right, you need to convert it into a one-dimensional or a fully connected network. So before that, we need to convert this data into a flattening data. So that's what this flatten will do, to convert the image or two-dimension data into one-dimension data. And then from layers, convolutional, like, okay, basically I'm trying to import convolution 2D, two-dimensional convolution. And so here I am using the max pooling, a two-dimension max pooling. Okay, so here basically, like, I'm setting the image ordering dimension as th. That means basically I need to represent the data weight matrix in the th format. Okay, so that's what it means. Like, okay, so in what order? Like, okay, whether you want to consider first number channels as the first or channels as the last. Okay, so since it's a two-dimension data, it doesn't have like multiple channels. So I'm trying to load this data. So rest of the format is exactly similar. So here I'm loading the data. So here, like, okay, so in the first case, right, we try to reshape it into, like, okay, so 784. Okay, one dimension vector. Here I am trying to keep as it is. Okay, so I'm trying to keep it as a image itself, a image of size 28, 28. Okay. So what I'm trying to tell you is, like, so try to reshape the data into a one channel, that is it's a grayscale image, each of size 28 by 28. Okay. So, and again, these images I'm just trying to convert into in the range 0 to 1. Okay. So white train. So basically, I'm just one not encoding the Y parameters. I'm trying to define the number of classes is 10. Okay. Here I am trying to define the network architecture. So the model is a sequential model, that is a feed-forward model, feed-forward network. Model.add. So I'm trying to add the first convolution layer here. Okay, model.add. So what kind of model? Like, I'm not adding a dense network now, dense layer. Okay, rather than I am adding a convolution layer now, convolution 2D, two-dimensional convolution layer. So what is the parameters here? Like, okay, so I'm trying to add a first convolution layer with 32 number of filters. I'm trying to consider 32 filters. Each filter is of size 5 by 5. Okay, so in the first convolution layer, I am trying to use 32 number of filters, and each filter is of size 5 by 5. Input dimensions, what is the input dimension? My data is a 28 by 28 image. Okay, and first, after this, I am trying to use activation. Within the activation, I am using ReLU as activation function in the convolution layer. Okay, so it does two things. One is it performs the convolution and do the ReLU activation. Okay, followed by I am trying to add a pooling max pooling model.add max pooling 2D. Okay, so pool size. So what is the size of the pooling window? It is a 2 by 2 window. Okay, I'm not specifying any stride. So if you don't specify the stride anything, like, okay, so it will take by default, it will take stride as 1. Okay, so here one more thing I'm just trying to add, like, okay, model.add dropout. Dropout means, so it will try to randomly remove some of the parameters. Why? Because if I this is a regularization parameter. If your model is tending to overfit, right? So you try to use the dropout to remove some of the parameters from the network architecture, or the learning parameter from the network architecture, so that, like, the network will not get into overfitting stage. So here I'm trying to specify, like, okay, so 0.2 dropout. Okay, so after that I'm just flattening the data. So whatever the data comes out of this pooling, right, after dropout, I'm just flatten it. Once the flattening is done, so I get a one dimension vector. So now I am adding a dense layer. So this is a hidden layer. Okay, so model.add a dense 128. There is 128 number of hidden layers, hidden neurons, and activation is a ReLU. And this is the output layer. Model.add dense, number of classes is 10. Activation is softmax. Okay, so until this, so the first convolution layer, pooling and dropout. This is where you are doing the feature learning. Okay, so these last two stages, right? These two is performing a classification. Okay, so feature learning and classification. Hence, it is a deep learning. Like, okay, so though it is a deep learning, like a deep architecture, I have used only one convolution layer and one pooling layer. So but like this, like, okay, for your application, if you want to add more number of convolution layers, right, you can keep on adding it. Actually, we'll see, like, okay, so one more large architecture I've taken. So little slightly bigger architecture. So this is how you can do it. And then model.compile. I'm trying to compile the model. Loss is categorical cross entropy. Optimizer is same, Adam, and accuracy. So rest of the things are same. Okay. So one convolution layer with 32 filters, 5 by 5. Each each filter is of size 5 by 5. So I'm using max pooling, and dropout is optional. Like, okay, if you don't want to use the dropout, you can just omit it. I just wanted to show you, like, okay, so how to use the dropout or the regularization parameter inside the network. That's the reason I used it. Okay. Then rest of the things are exactly similar. Okay, so I'm just fitting the model here with training data. For validation, I'm using the same test data. Number of epochs is 10. Batch size, I'm trying to take 200 images. So be careful, like, okay, when you are using a GPU, right? If you are using a GPU, and if your GPU memory is right now, like, okay, so I'm running in a CPU, it doesn't matter. But when, especially when you are using a GPU, so ensure, like, okay, so your batch size is appropriately decided. Okay, if your GPU memory is less, and if you give a large batch size, it won't be, entire data won't be fit into the GPU memory. Then you will get a CUDA out of memory error. So you may get it that kind of error. So depending on, like, okay, so what is the size of GPU memory, you can decide the batch size. And here I am trying to compute the score. Okay, so we'll just try to run it. So since I am running on a CPU, it might take slightly more time compared to the previous case. So the concept is very simple. Like, okay, so this is what I said. Like, okay, so or like, okay, so implementing a deep learning solution for your own problems, right? It's very straightforward. You need not to write extensive or very lengthy programs. Okay, so everything is already available. You can just use it. Okay, so at least, like, okay, so in this case, we are writing at least some code. There are cases where, like, you need not even write any code also. So already, like, okay, so there are some systems available. Like, okay, so the packages are available. I think deep cognition AI, and if you are trying to use those kind of tools, right? Even Samsung has got uh, our own platforms. Okay, so which is you can use for a trial basis. Okay, so freely for about 2 months. Okay, so you can Brightix, call it as a Brightix. So where, like, okay, so it's all UI interface, web and UI interface. So where you can drag and drop the network architecture and build the solution. You can just load the data, select the standard architecture, or, like, okay, so custom architecture. You can drag and drop and initiate the training, and the things will be done. Okay, you need not to even write the code like this. Okay, things are very simple. What it is required is, like, okay, so when you start looking into the analysis, when you start analyzing the data, right? How did I get this solution? That's where you more emphasis or more insight is required. Otherwise, writing the code itself is very simple these days with all these kind of tools. You can even observe here, right? Like, okay, so it is every time the batch is updated by 200 in terms of 200s, because we set the batch size as 200. That means in every iteration, it takes 200 images as one batch. I'm sure, like, okay, so you might have discussed yesterday, like, so what is the impact of batch size, what is iteration, what is epoch, how the weights will be updated, and how the back propagation happens, and all those things. Okay, so let us not get into those details. I think you already discussed. Okay, maybe after one epoch, I will just stop it because it is taking too much of time. We will see, like, okay, so few more programs. So just now it completed 1 epoch. So after 1 epoch, so the validation loss is 0.081. So you can clearly see, like, so even only after the first epoch itself, it is almost 97%. Obviously, this will give like much better result than the previous case. Okay. So I just stopped it. So maybe I will share this code. You can just try to execute in your offline. And if you have any problem, let me. So this is same problem, but I have considered like so slightly bigger network architecture. So without spending too much here, like we shall slightly look into the directly look into the model. So again, here I'm specifying it's a sequential model. So first convolution layer, like I'm trying to specify the number of filters as 30, each of size 5 by 5. So input size is same. So I'm using the activation as ReLU. So followed by a max pooling. So again, size is 2 by 2. So then followed by one more convolution layer. In the second convolution, it has got 15 filters. I have added 15 filters, each of size 3 by 3. Activation is ReLU, followed by pooling. Then I'm using the dropout, flattening. So then dense layer. Okay, so it has got two hidden layers, like okay, so one first hidden layer, second hidden layer, and followed by output layer. Okay, so basically, like okay, so compared to this previous case, here I have added one more convolution layer and a pooling layer, and then so even in the output case, right? So even in the fully connected layer, instead of having one one hidden layer, I have added two hidden layers. Okay. So this is how you can keep experimenting with different type of architecture. You can just vary the number of filters, number of size of the filters, and like okay, you can add the number of layers, also convolution layers. Okay, so you can even try out with the different activation functions. Like so, ReLU is one activation function I've used. Like we say like this, you can start using different activation functions. And similarly, like okay, so when you're in the optimization side, you can use the different loss functions. Like, so you have different loss functions like okay, so cross entropy, categorical cross entropy, MST, and again in optimizer, like okay, so you can use the different type of optimization techniques and try to do the experiments. So this is how like so you can implement. So I will try to show it for the one more case. This is image classification. Okay, so this is I worked on CAFR data, CAFR 10 data. So this is about 10 class color image data. Like each image is of 32 by 32. Okay, so totally it has got 60,000 training data and 10,000 testing data. So I think probably you might have seen the CAFR data. Like if you have not seen this, I'll just show you. So you're able to see the screen?
Yes, sir.
Yeah. So this is what like we so CA for data set, like it has got 10 classes like aeroplane, automobile, bird, cat, etc. Right. So these are the generic images. Each image is a color image here. So unlike the previous case, right? These are the color images. It's a 3-channel image, and the image size is 32 by 32. So again, like okay, we are trying to do the. So here what I'm trying to define the network architecture. So model is a sequential model, convolution 2D. Like so, the first layer has got 32 layers. Sorry, 32 filters with filter size is 3 by 3. So input shape you can see here. Like so, in the previous case, input shape was 1 comma 28 by 28. Here it is a RGB image 3 comma 32 32. Activation like okay, so I'm using ReLU. And one more thing, like okay, I'm using padding here. Okay, so padding means so if you want to consider like okay, your output image after the convolution is same as the input image, right? You need to add the padding. Okay, so either you can add the padding as zero padding, or the same padding means it will replicate the columns actually. So here I'm using the dropout at individual layers. Okay. So you can add any number of dropouts and any number of times. Okay. So just to showcase, like, okay, so different ways of using. So this may not be like, okay, so the meaning for this network architecture. I'm just trying to showcase you, like, okay, so how this can be implemented. Okay. So I'm adding one more convolution layer. Second layer has got 32 filters again, 3 by 3. Activation is ReLU. So followed by pooling, and then it has got third convolution layer, which has got 64 filters. Each of size of each filter is of size 3 by 3. So fourth convolution, fifth convolution, sixth. So totally it has got 6 convolution layer, followed by flattening, and then dropout. Okay. So this is how, like, okay, so I have we have created it. Okay. And then so here, like, okay, so the for the optimization I'm using the SGD. Okay. SGD as a standard gradient, stochastic gradient descent as the algorithm for optimization, and loss is categorical cross entropy. And one more thing, like, okay, all of you are familiar with the last learning rate, right? Learning rate is like, okay, so basically how you control your learning. Okay. So the learning time, like, okay, so if you give, like, okay, very large learning rate, so there could be a possibility that the learning may not happen, or, like, okay, so it may get into the oscillations. And if you give very small learning rate, so the learning will be very slow. So your process of learning will be very slow. So this is a very common problem. Like, okay, so what should be the appropriate parameter for learning? So to overcome this, like, okay, in practical scenarios, we don't use the fixed learning rates. Okay, we try to make it as a function of the iteration of the effort. I use the same thing here. Okay, here the learning rate is initially, like, I set the learning rate as 0.01, and I am specifying, like, okay, so as the number of iteration increases, right? So the learning rate becomes smaller and smaller. So I'm trying to divide it by the number of epochs. So that, like, okay, so the decay, or, like, okay, so the learning rate will keep change over a number of epochs. Initially it start with bigger learning rate. As we increase the number of epochs, right? So the learning rate will become smaller and smaller. So that's what I am trying to define here. And rest of the process is same. So it will fit the model with the training data, and validate or the test with testing data. Okay, so this is what about the object classification. So finally, like, okay, so to end, I will just demonstrate or run through the autoencoder code. Okay, probably we will run this just to see the result. Okay, so here we are trying to implement the autoencoder, especially for the image reconstruction. Okay, so this can be considered as a image compression or the dimensionality reduction technique. Okay, so as we discussed, right, like, I'm taking the MNIST data. MNIST data is having totally 784 pixels. Okay, this 784 pixel, I want to latent encoding, I want to keep it only 36. Okay, so that means the 784 dimension data need to be reduced or, like, represented by only 36 data points. That's what the meaning here. Okay, so this is what my input image shape. So that is 784 rows. So I am trying to encode. In the encoding, I am using a dense layer. Okay, encode here I am not using a CNN, but I am using the conventional approach, but you can still follow the same. Like, okay, so while defining the network architecture, right, you can even use the CNN kind of approach. Okay, here what I'm trying to do is, so encoding dimension is I would set it as 36. I want to encode this encoded data into 36 layer, 36 neurons data. Activation is ReLU, but input is 784 data. So basically it takes 784 dimension data and encode it into 36 dimension data. Okay, so this is the forward pass encoder part. In the decoding part, I need to implement the decoder also. That means it's a reverse process. So decoder will have again it's a dense. So I need to decode into 784 data points. Okay, activation is a sigmoid, but the data is what is the input for this decoder is encoded data. All of you are able to get right. So for encoder, input is image data. I want to encode it to 36 dimension. For a decoder, I want to reconstruct it to 784 data points, but input is my encoded data. So autoencoder, it will starts with a model image data input image, and then followed by a decode. Okay, so encoder, this is the encoding, like, okay, so where I am trying to do the encoding. So it takes the image data and performs the encoding. So encoded image input is like, this is the encoded dimension. So basically, like, okay, we defined all these things. Like, okay, here I am trying to compile the encoding auto encoder. So input shape is like encoding dimension. Decoding is auto encoder dot layers -1. Like, okay, so basically, since we have only one layer, so the decoding layer, like, okay, so, or the latent representation is layer -1. Okay, auto encoder compiler. So compiling the auto encoder now. Optimizer is add delta rule. Okay, loss is binary cross entropy. This is another loss function. So what I'm trying to do is, like, okay, I'm just trying to load the data, MNIST data. I'm trying to reshape it. Okay, this data. So here I'm fitting the autoencoder model. So basically, I'm trying to take X train, Y train data. So I'm running for 50 epochs. Batch size is 256. Shuffle. So basically, whether we need to shuffle the data or not. Okay, so I'm just for the sake of, like, okay, so showcasing, like, okay, so how to shuffle the data. I'm trying to shuffle the data, and validation, I'm using the rest data. So here I'm just trying to reconstruct, like, displaying the reconstructed images. Okay, so we'll just try to run this and to see the result. I think probably while it is running, if you have any questions, I think probably we can discuss until it completes the running process.
Some questions are there.
Yeah, yes, sir. Yeah, yes, sir. Please.
How do we solve the overfitting problem in deep learning?
So overfitting problem, like, okay, so we try to solve using this dropout. Dropout is one regularization approach where we try to randomly drop some of the parameters, like, okay, so some 20% of the, or like whatever the specified number of parameters, to avoid the overfitting.
So what is the difference in these platforms, that is PyTorch, TensorFlow, and Keras?
What is that? Like, can you please repeat?
Difference in platforms such as PyTorch, TensorFlow, and Keras.
So see, these are the different packages. Like, okay, so TensorFlow, which is developed by Google, like, okay, so, and PyTorch is being developed by Facebook. So it has got, like, okay, so different facilities. Like, okay, so if you look into the deep learning development, right? Like, okay, so earlier we used to use the Theano and then Cafe, so which are specifically defined by, like, okay, so from the university fraternity for a specific kind of cases. Like, okay, Cafe was specifically built for image data, so which has got, like, so more of a C-like code. Okay, so then the TensorFlow picked up the speed, like, okay, so the people, it started becoming more popular because TensorFlow can support not only the image data, even the other forms of data. Okay, and initially, like, Keras was separate. Like, okay, so Keras was a wrapper. Okay, so which takes Theano or TensorFlow as a backend, and started like, because if you write a code in TensorFlow, right, like, it won't be very straightforward like this. So since, like, okay, we are using a Keras as a wrapper, like, it becomes very simple to write it. Okay, so similarly, PyTorch, like, it offers different kind of flexibility, especially for the image data. So where you can even train the point clouds. Say, for example, 3D point clouds. Like, okay, so if you have a 3-dimensional data, right, the depth data, X, Y, and Z point cloud data, even you can try to train the models using those kind of point cloud data. So where 3D convolutions and everything is implemented, which is very straightforward to implement. So it's all, like, okay, so more than sticking into any kind of these kind of platforms. So it's all about the forum. Like, okay, so for example, which research community, what is the number of researcher or the research community using this tool? Like, okay, if you're stuck with, because these are all open source, right? So you may not get proper documentation or support from the developers. Okay, you need to rely on the forums. Okay, so in these forums, like, okay, so what kind of support you will get it, and what is the simplicity of using it, okay, how efficiently you can build it. So that's what, like, that's what drives the thing. So in other words, if you look into, like, okay, Cafe, TensorFlow, or PyTorch, all are, like, okay, so platforms, like, okay, say a Python based framework which will help you to build, like, okay, so deep learning models, and you can, it will assist you in loading the data, training, and exporting the model. Okay, so that's where, like, okay, you need to decide, like, okay, so what kind of platform should be used. So it all depends on your convenience and, like, easy to use it.
Is there any interpretable classifiers available currently?
So interpretable classifier in the sense, like, okay, so what exactly you are referring to?
Interpretable for classification.
So interpretable, like, so there are, like, if you look into the, if you're talking about the interpretable AI, so there are class activation maps which are available. Like, so we call it as a grad cam and class activation maps and gradient class activation maps, which will identify, like, so which particular class the image was classified on what basis. Those will be, like, okay, highlighted. Like, okay, you can visualize, like, okay, so which part of the image was analyzed and which part of the neurons was triggered. So those kind of information you can visualize it. Again, like, okay, those things are even still available in the TensorFlow also. You can just add those as a class activation maps into your network architecture, and you can visualize those parameters.
Can we use a PyTorch for medical image analysis?
No, you can use, like, okay, so even you can use TensorFlow also. You can use PyTorch, you can use the TensorFlow. Anything is fine. Even for that case, even you can use the Cafe also. There is absolutely no restriction, because Cafe, PyTorch, or TensorFlow will not restrict you. Like, for that, it is still a image. What kind of architecture and how do you build the architecture, that is up to you only, whether you want to use the standard architecture. If any specific layer or, like, okay, any specific parameters is not implemented, then probably you need to look for the other architecture, other platforms. Otherwise, you can use any of these platforms.
Why ReLU cannot be used in the output layer?
See, basically, ReLU, like, in the output layer, like, okay, our objective is to classification. ReLU is only, like, okay, you are trying to kind of doing a kind of normalization. Like, okay, you are trying to segregate. Okay, so negative, all negative values. In case of final layer, my objective is not to segregate negative values or the positive value. I want to classify the class, like, okay, so to which class it possesses the maximum probability. That's the reason in output classes mostly we use softmax.
Okay, sir. No more questions.
Yeah. So these are the I just completed the running. Like, okay, so the first row is the input images. These are the images which were considered, and the second one is the 36 pixel representation. Like, so though the size is same, but you can see, like, okay, the pixel sizes are different. Like, okay, so these are the 36-bit representation. 36, not 36-bit representation, 36 data point representation of 7. And the last row is the reconstruction. Like, okay, so from 36 data points, when I reconstruct the image, so this is how I could able to reconstruct. Okay, so the input is the first row. So the middle one is the encoded data. Third one is the last row is the decoded data. So you can clearly see, like, okay, so in almost all cases, we are able to reliably reconstruct it from the 36 data points. That means this 36 data points is good enough to do the classification. Even you can use these 36 data points for your classification, any classification. That way, you can treat it as a dimensionality reduction, or it can be used as a data compression technique, etc. and so forth. So similar way, you can give, like, okay, so the image and its noise pair, and you can realize, like, so the noise free output image, etc. and so forth. Okay, so the code or the architecture looks exactly same, but only thing is you need to change the input output pairs, like, so that you can easily realize the different solution. Okay, so I think this is what I just wanted to cover as part of today's discussion. So if any further question or anything, you can just ask me. Otherwise, like, I will share this code to the organizers. I think probably they will distribute this code to you guys. So if you can use it, you can run it. If you find it any difficulty in running this, or if you want to customize this, let me know, so that I will help you out in offline.
Okay, sir. Thank you, sir. So here we come to the end of the day 5 session. I, Professor Mohammad Saifuddin, on behalf of Department of CSC PACE, feel privileged to wholeheartedly extend my gratitude of having Dr. R. Dinesh, Research Scientist, Samsung R&D Bangalore, as the speaker of today's session. I'm sure the fine-grained theory concept followed by an excellent hands-on session by the eminent speaker would have given all the participants a complete exposure in materializing and understanding even the highly complicated topics in a simplest way. I affirm that all the participants will have a lot to take away from this highly knowledgeable session and help have an exponential leap in their research progress. Thank you for such a wonderful and highly informative session, plus for the patience and earnest attempt to reach every enthusiastic mind. Thank you, sir.
Thank you. Thank you very much.
So here we come to the end of day 5 session. So dear participant, thank you for your active participation throughout the day. Before leaving the meeting room, I request all the participants to give their feedback of today's session. We shall be back tomorrow morning at sharp 9:30 a.m. with a fresh mind to observe the new concept. Links for the material shared by our speaker will be shared to all the participants as we receive it. Thank you, one and all.